Welcome, everyone. Today, we'll explore the exciting new features and major advancements introduced in the latest release of ANSA 2025.1. This release brings a host of enhancements across multiple domains, including the new user experience, modular environment, model build, geometry, meshing, CFD, isogeometric analysis, crash and safety, results mapping, durability, composites, design and morphing, optimization, SPH solver, kinetics, electronics, electromagnetics, user productivity, AR and VR. So, without further ado, let's delve into the features regarding the new user experience. Let's begin with one of the most noticeable updates, the introduction of the dark theme. This long-requested feature is designed to reduce eye strain during extended sessions and enhance the overall user experience. As for the settings, a new structure has been introduced, replacing the old layout and adding support for profiles. Profiles offer a cleaner organization, easier sharing, and consistent behavior across different environments. It's also possible to create a team profile to enable collaboration among multiple users. Moving on to the next key enhancement, interactive customization of the ribbon tabs. This new feature allows you to dynamically configure the ribbon interface without the need for scripting or advanced setup. Tools and functions can be easily organized to suit your workflow. Reposition functions as needed, tile them horizontally or vertically to create a ribbon layout that matches your preferences. Let's now move on to the modular environment. Submit simulation runs locally or on remote HPC servers and monitor solver status and logs in real time through the solver submission tool. Remote submission is available only when ANSA is connected to an SPDRM Backend 2025.1 version. Leverage the new Build tab in the model browser to add breakpoints and reminders and get a bottom-up view of all build processes. Through the Graph View tool, it's possible to visualize assembly connectivity by clearly showing every subsystem and the intermodular connectivity links between them. The assembly diagram can act as the primary model view, even when the full FE models aren't loaded. The NVH simulation platform enables end-to-end management of full vehicle NVH workflows, including automatic generation of reduced models from pre-configured settings, efficient methods for creating what-if scenarios, built-in version control and traceability through a structured data management system. Lastly, starting from the regular subsystems stored in the data management system, you can generate display and reduced models using the dedicated, simplified DM browser actions. These actions apply predefined presets, also stored in DM, and automate the creation process. The resulting reduced models can then be submitted for execution either locally or on HPC systems. Now, let's move on to model build. Let's start with an exciting new capability in ANSA, the geometry-based machine learning part type detector. This feature introduces a powerful, pre-trained ML classifier that can automatically identify the part type based on 3D geometry. The classifier can recognize a wide range of part types, including sheet metal, casting, extrusion, tube, fasteners, and solids. This is especially valuable when the part type isn't clearly defined in the PLM system, or when existing data is unreliable due to poor quality or high complexity. We've introduced a new capability that allows users to import substructures directly from INP or ANSA files. What's more, the transformation matrix is automatically calculated based on any transformations applied to the substructure. Additionally, the substructure property of each instance is automatically updated according to its transformation matrix. Regarding geometry, we're introducing an innovative tool developed to enhance mesh generation workflows. It automatically identifies and connects faces based on spatial proximity. This significantly streamlines the process of generating volume meshes with node-to-node connectivity. With this release, users can project existing geometries directly into sketches. Users can now apply constraints and dimensions to these imported projections, enabling full parameterization and greater control. We've also introduced the ability to now easily create sketches by cutting a section of 3D geometry. The parameterization of that section can be performed using constraints and dimensions. This not only improves accuracy, but also significantly boosts productivity when working with complex geometries. Sketches now integrate seamlessly with the ANSA Transform tool. After a transformation, all constraints and dimensions are preserved, and the sketches update automatically. Regarding meshing, the new Mesh Settings user interface has been designed to guide users more intuitively through the mesh generation process. It helps select the most suitable mesh setup depending on the model type. Additionally, variable sizing is now supported across all model types, offering more flexibility to adapt the mesh to geometric and physical features. We have introduced advanced controls in the quad-dominant meshing process. These controls allow users to prioritize minimizing the number of triangles, with less emphasis on quad orthogonality and element length precision. This gives more flexibility to tailor the mesh quality based on specific project requirements. The new surface split functionality under the Decompose tab will allow you to decompose your solids using existing planar surfaces with single clicks, avoiding tedious selection steps. A new option in casting now treats tubes with increased accuracy, significantly reducing improvement time and enhancing overall simulation precision. Consistent and accurate middle mesh generation is now supported on single-bound fillets, based on the user's preference. This enhancement improves control and precision in mesh creation for complex geometries. Middle curve creation is now supported for complex profiles, especially useful for casted parts like grills. The process involves generating a middle curve directly from a face, which is then extruded. Now let's move on to some updates on CFD. Regarding support for the Fidelity CFD solver, the case setup window has been redesigned to allow easier definition of boundary conditions, materials, and solver settings. Additionally, Fidelity CFD materials can now be defined directly within ANSA. Finally, the case can be exported in the native ADIO S2 format. A new function has been added to the geometry ribbon for the easy generation of standard domains, such as a box, sphere, bullet, or supersonic domain. In Batch Mesh, fields now support ANSA parameters, allowing for easy tuning of mesh settings and straightforward setup of mesh refinement studies. Additional improvements include enhanced quality for anisotropic meshing. Moving on to auto-seal improvements, these include automatic PID assignment for the created patches, a reduced number of generated elements, overall better patch quality, faster processing, and lower memory consumption. For Hexstream, there are improvements in volume mesh quality and gap capturing. Users can now choose between high or low resolution in gaps, allowing either better feature capturing with more elements or fewer elements with faster results. Layer generation offers more controls, providing greater flexibility. Finally, users can define the quality criteria to be respected during Hexstream execution. For Hexablock, a new tool has been introduced to enable easy block generation and meshing for Gerator pump geometries. Additionally, the Airfoil tool has been enhanced to automatically generate block-structured mesh for multi-element airfoils. Finally, a new template has been added to the Turbo tool for block-structured meshing on centrifugal pump volutes. Let's take a look at what's new in isogeometric analysis. The IGA quality check has been enhanced with a new parameter called Check Invalid Edges. This addition enables the identification of invalid, self-intersecting, sharp and zero-length IGA edges. Furthermore, it is now possible to create more realistic models by mapping the keywords initial strain, IGA shell, and initial stress, IGA shell. The IGA ribbon tab has been expanded with new functionality. Since geometry editing is often required for large components, the Zone Cut feature has now been added as a button within the Edit Geometry group. For the same reason, the Plane Cut button has also been added to the Edit Geometry group. Additionally, a new Edge group has been introduced in the IGA ribbon tab. This group includes functionality for creating 3D curves based on the IGA Edge UVW keyword. The Edge group in the IGA ribbon tab has also been expanded. In addition to creating 3D curves from the IGA Edge UVW keyword, it also supports the creation of points using IGA Point UVW or 3D geometrical points. Users can define these points with control over either their total number or the distance between them. To support a better understanding of IGA quality, the Shell Patch Info feature now visualizes the underlying control polygon net of an IGA 2D Enerbius XYZ surface. On the other hand, the contact check functionality has been extended to support IGA shell patches and now identifies intersection issues. The contact check also identifies penetration issues and issues of projection in tied contacts. Regarding assembly, the Connection Manager now supports the Hexa contact finite element representation for seam lines and adhesives. Furthermore, it is now possible to directly create beam elements of spot weld material between IGA flanges. These are automatically paired with a corresponding contact spot weld. In continuation of our support to the IGA solid, IGA dev volume entities, morphing is now supported through ortho boxes. To conclude, the keyword Load Edge UVW is now supported for the direct application of uniformly distributed loads on a parametric edge or a set of parametric edges. Additionally, Load Rigid Body is now supported, enabling the application of concentrated forces to IGA entities defined with rigid materials. Now, let's explore the latest in crash and safety. Let's start with the Airbag Folder tool, a new approach for setting up airbag folds. It simplifies the process and supports model building for both PAM Crash and LS Dyna. The Luggage Impact tool is now introduced to support the ECE R17 regulation and other custom luggage positioning cases. This regulation checks whether vehicle seats can withstand luggage impact during a crash, helping prevent intrusion into the passenger area. Two new seat positioning tools have also been added. The Seat Field Positioning tool generates standard seat kinematics based on seat frame points. The Seat Point Positioning tool, on the other hand, allows custom seat kinematics by matching specific points. The Landmark Positioning tool automatically aligns the dummy by matching key landmarks to target positions based on physical test data. This ensures accurate and consistent dummy placement. For pedestrian safety, the corresponding tool now supports a wide range of new regulations and protocols. This ensures that simulation setups remain compliant with the latest standards. We continue with the Low Speed tool, which now also supports the GB 17354 protocol. Finally, PAM Crash 2024 is now supported. Now, let's take a look at some updates related to results mapping. In the Results Mapper, users can now directly map scalar, vector, or tensor data from solver results to temperature, pressure, or stress conditions. The data scanning process is handled through Meta. In the Results Mapper tool, support for ProCast results has been added. These results can be formatted for use in CrackFem software. The NTL results file can now be used in the Results Mapper to map results such as porosity, liquid to solidification, and cast length, enhancing the versatility of the mapping process. Next, we'll cover updates in durability. The new SeamWeld Designer introduces a stepwise and highly flexible tool for defining SeamWeld finite element representations tailored to your modeling needs. It supports a wide range of weld types and gives users full interactive control over root and toe locations, element types, and the number of connected bodies. Crucially, it accommodates both mesh-dependent and mesh-independent representations, offering full flexibility within the modeling workflow. The Load Case Assistant is now available for both ANSYS and OptiStruct decks. This tool provides a single, intuitive interface where users can define all supported boundary conditions, loads, simulation data, and more, all in one place. It simplifies setup and ensures consistency across different solvers. A new visualization mode through Check Contacts is now available. With this new visualization mode, the user can review the contact status with a fringe plot by retrieving the C-status from Abaqus results. The Fringe Plot tool now includes the option to visualize the cross-sectional properties of beam elements. In the Beamify Structure function, a new capability has been added to the domain definition. Under the Location option, users can now use the new Recognize button, which automatically identifies beam-like structural areas and generates the corresponding paths for model reduction, all with a single click. Additionally, in the Beamify Structure function, the Morph Boxes option has been replaced with the new Containers option. This enhancement allows users to select morph boxes, properties, materials, sets, includes, and ANSA parts during the initiation of pick mode. In oil canning, several new options have been introduced. First, users now have the option to skip the linear static or normal modes analysis and run only the nonlinear static analysis. Furthermore, a move back option has been added for further depenetration between the impactor and the impact area. A preview option has been added in static, nonlinear critical points, similar to the normal modes, nonlinear critical points function. Also, a critical points area setting has been added in normal modes, nonlinear critical points, where the user can define a set of elements where the critical points can be located. This option allows for better detection of the target points where the impactor can be positioned. For the tie contacts, new functionality to update the position tolerance field is now available. The automatic update is based on the calculated minimum distance between the primary and the secondary surface. This functionality is available both in the context menu of the tie list and Inspect Contacts function. The definition of shell-to-solid coupling has been enhanced with improvements not only at the detection level, but also at the inspection stage. More specifically, right after the initial detection of the area of interest, the user is prompted to edit the definition on the fly in order to achieve the desired outcome. The keyword beam general section equals meshed is now supported in conjunction with section stiffness, section inertia, transverse shear stiffness, and section points. By creating the cross-section and then running the beam section generate analysis, the beam property section equals meshed can be created. Non-orthogonal concentrated load definition is now supported for Abaqus, ANSYS, and Adventure cluster solvers. A concentrated load can be defined easily by just selecting 2 points or nodes from the screen and adding a magnitude value. New functionality is also available to automatically or manually merge concentrated loads defined on same node and step. Let's take a look at what's new for composites. A new RVE type is now available, Foam from Retomo. The RVE generator can create RVE models with the information that comes from Retomo CSV file. Retomo can export a CSV containing geometric features such as shape and location of recognized voids and orientation of fitted ellipsoids. Now, let's explore enhancements in design and morphing. 2D ribs can now be quickly generated by selecting points or curves, establishing automatic connection to adjacent elements. Additionally, ribs can be copied, bent, and split along their draw direction, once again ensuring automatic reconnection to the model after modification. Multiple checks can be performed on 2D ribs to identify definition and manufacturability errors. Additionally, dimension checks for pockets between 2D ribs and the base surface are available. Any issues detected can then be corrected. Subdivision surfaces for beam-like structures can be effortlessly generated using the wrap function. A new control cage is fitted around the visible elements by detecting the principal axis of their cross-section upon mouse hover. Subsequently, the corresponding sub-D surface is automatically constructed. Feature creation of beads and stamps allows creation of initial stamping results. The supported results are stress, strain, thickness, as well as creation of a property, indicative of the initial shape and dimensions of the initial blank of the feature. The stamping results are calculated using the inverse forming tool. Direct and box morphing support non-uniform scale transformations, allowing differential scaling factors to be applied to each axis of the model in a controlled and independent manner. Moving on to the latest developments in optimization. Efficient global optimization algorithm falls under the category of Bayesian or adaptive optimization. This type of optimization combines direct and RSM-based methods to reach an optimal design, performing both exploration and exploitation of the design space. EGO is one of the most popular adaptive sampling algorithms for global optimization of simulation models. Custom optimization algorithms written in Python can now be implemented in ANSYS optimization tool to define and run optimization studies. Upon selection, a dedicated interface will open, where users can add their algorithm according to the tool's specifications and requirements. An example is also available to help guide users with the setup. Moreover, users can now customize the selection of simulation runs to be used for RSM training, from a single or multiple DOE studies. ML models, or RSMs, can be directly used to new DOEs before running the actual analysis in order to evaluate the DOE or to verify the RSM's accuracy. ML predictors trained on 2D curve and 3D full field results can now be employed as task items of an optimization workflow. This means that we can use them instead of solvers in an optimization study, perform our own post-processing on the results, and get to the predicted optimum much faster. Parallel calculations of experiments are now possible for direct optimization studies. Parallel calculations are supported for evolutionary optimization algorithms, differential evolution and NSGA2 that generate populations of experiments, and gradient-based algorithms, CG and SQP, for the estimation of the gradients. The GMesh, Impetus, and NX-Nastran solvers are now supported as the FE output of the pre-processing of an optimization task. Furthermore, optimization studies can now be solved in optimality. Optimization cases with discrete design variables can result in optimized DV values that fall between allowed options. The previous approach adjusted each value to its nearest acceptable discrete level, which risked overlooking better performing valid designs. The polishing process instead evaluates all combinations of the nearest acceptable discrete values for each such variable, resulting in 2 to the power of n candidate designs for n discrete variables. Now, let's take a look at the new features in the SPH solver. In ANSA 2025.1, a new thermal solver has been introduced for SPH simulations. This enhancement allows users to explore the effects of thermal variations in complex scenarios, such as gearbox simulations. The fluid begins at its lowest temperature and gradually heats up due to gear interactions, transitioning through white and orange to indicate rising temperatures. Notably, in ANSA SPH 2025.1, fluid viscosity can now be temperature dependent. Users can define custom models or import lookup tables to accurately capture how viscosity decreases in high temperature regions, such as near gear teeth. ANSA SPH solver now supports multi-phase simulations, enabling the modeling of interactions between fluids with different properties. This capability opens the door to simulating a wide range of real-world engineering problems where multiple fluid phases coexist or interact. Over time, a filament forms and becomes unstable, eventually breaking up into small droplets, demonstrating the Rayleigh plateau instability in action. During SPH simulations, viscous forces play a critical role in both the stability of the solver and the overall simulation time. Using innovative numerical techniques, ANSA SPH solver can simulate viscous fluids even with relatively large time steps, maintaining stability and improving performance under challenging conditions. Additionally, the introduction of a user-defined viscosity function provides flexibility to simulate non-Newtonian fluids. The SPH solver supports sensor monitoring, allowing users to visualize simulation results in real time or post-processing. We introduced surface sensors, a specialized type of sensor that maps key physical quantities directly on the mesh. Finally, significant progress has been made to reduce simulation time without compromising accuracy. We continue to push the boundaries in developing high-fidelity SPH models that run faster and more efficiently. In version 2025.1, Solver is now up to 2 times faster compared to the previous release, delivering substantial gains in speed and productivity. Let's explore some updates in kinetics. The newly introduced frequency response analysis enables users to examine how the system responds to excitations at different frequencies. By applying an input signal, such as a swept sine force, you can evaluate the system's response, such as the displacement at a specific location, over a specified frequency range. Moving on to electronics. Based on the output generated by the ECAD importer, a dedicated tool has been developed to mesh all PCB components and accurately represent pins, underfill, and solder mask. Upon completion, the PCB is fully meshed using a highly structured mesh, ensuring detailed and precise modeling. The names of the materials used for each PCB layer are now directly imported from the IPC file. Additionally, further information is provided in comment field of the materials card. In previous versions, the reading of the PCB layer started from the first conductive layer. Now, the solder mask is also imported if it referenced in the IPC file. A different color is assigned to make it easier to distinguish from the other layers. The performance of the ECAD importer has been significantly enhanced during trace mapping. This has been achieved by storing the element's metal fraction using the DB storage functionality instead of the metal fraction user attribute in the element's card. Thermal components of JEP30 format can now be imported, with simultaneous creation of thermal network data for Fluent. The possibility to preserve the thermal components' footprints on the board is also provided. Finally, this release introduces several new capabilities to support advanced laminate modeling, specifically focusing on metal fractions at the element level. First, we now support multi-phase material definitions on a per-layer and per-element basis. In addition, we calculate and track the volume fractions of each material phase within every element. We've also introduced a volume fraction fringe bar for visualization. And finally, all this detailed element-wise phase data can be exported for use in simulation, enabling runtime homogenization. Let's move on to the latest in electromagnetics. ANSA now supports the Clarity Electromagnetic Solver. To facilitate this, a dedicated ribbon for electromagnetic model preparation has been introduced. This ribbon includes, among other functions, a ready-to-use checks template that meets the requirements of the Clarity Solver, as well as an output function that exports the FE model from ANSA in a file format directly compatible with Clarity. Now, let's explore features that boost user productivity. We've introduced new transparency control options. You can enable transparency and adjust it individually for different entities in the model, such as FE mesh, meshed faces, and unmeshed elements. This provides a clearer and more comprehensive overview of the model. We've introduced several enhancements to the entity cards, allowing you to perform key actions, such as show, hide, show only, new, reference, highlight, directly from the card itself. It's also worth noting that a red triangle appearing on specific fields indicates an undefined entity. Regarding the include files, there is now an option to output only the modified lines, allowing for more efficient management of changes. The reference function has been redesigned to include upstream and downstream results with improved performance. Several selection enhancements have been introduced to make selecting entities easier and more intuitive, along with improved hover previews. From the selection toolbar, the new plane selection feature allows you to select entities using a reference plane. Simply define the plane and adjust the distance over which the selection should extend. Additionally, a hover preview is now available for polyline, polyarea, path, opposite path selection, giving you a clear visual indication of which entities will be selected before you confirm the action. Moving on, right-click actions are now available for all functions, depending on the selected entity. By right-clicking in the graphical area, a contextual menu appears, providing quick access to relevant functions as well as a list of recently used ones. The embedded Python interpreter has been upgraded from version 3.11 to 3.13.3, giving users access to the latest language features and improvements. Additionally, NumPy has been updated to version 2.2.3, and the documentation for the Python API has been significantly enhanced for better usability and clarity. Moving on, the compress function previously removed only unused entities. Now, similar to the functionality in the material card, it is possible to compress shell or solid properties based on their name or values. This means that even if these properties are in use, they can still be compressed, as long as they share the same name or identical values, helping streamline and clean up your model more effectively. It is also worth mentioning that user actions are now available through a new script that allows for custom user actions in the material database. When it comes to user productivity, until version 25, NX Nastran was supported through the MSC Nastran deck. In version 2025.1, a new NX Nastran deck is introduced, allowing the users to easily set up an NX Nastran model. This new deck will help users distinguish which keywords belong to which solver. Finally, let's step into AR and VR. With this release, the Varjo XR4 headset is now supported. What makes this special is the ability to seamlessly switch between virtual reality and mixed reality with just the press of a button, directly from the menu interface. This means all existing VR functionality is now fully supported in mixed reality mode as well, giving users maximum flexibility and a more immersive, context-aware experience. Thank you for watching.